Hello, everyone. This is me, Assam Hilmi. I will be your moderator in today's webinar. Today's webinar is titled Pressure Transit Fundamentals, Pressure Transit Analysis Fundamentals. I just want to confirm again that my voice is clear
Yes.
and that you are seeing my screen. Okay, thank you. I will be giving a short presentation about OBA. Then we will start directly to our session. Just a few minutes. This is Online Petroleum Academy, OBA Energy. In this presentation, I will give you very short notes about our upcoming service plans. This is a very beautiful dashboard for what we have done in the past years. You can see that we have more than 40 instructors joining us in providing professional technical courses. We have 3 teams in different countries here in Egypt, Lebanon, and Belgium. You can see that we are on the social media platforms, LinkedIn, Facebook, Instagram, and YouTube. I will not go through all this dashboard information. This is our second wave quarterly plan for the courses through January to March. We already started one of these courses, which is the rate transit analysis course, which is running up to today. We also have course pressure transit analysis in February from 11 to 16th with a break in the 14th. We also have a new course, which is well controlled preparation in March from 11 to 16 also in March with a break in 14 as you see in this screen. If you would like to register in any of the upcoming courses, you can scan this QR code. We also have a record of recorded courses which are available for any time at your convenience. This is a broad list of courses, 22 courses in different softwares and topics, which are very interesting, in PipeSim, GAP, RACAD, OFM, ISIS, Campus Sapphire, software, MBAL. If you'd like to purchase any of these courses, you will get a big discount. Just scan this QR code. We also provide interesting mentorship programs. If you have a case study or you'd like to get the recent and the updated experience and technology in one of the areas in the petroleum industry, you can contact us and you can design your own program to qualify yourself for your future plans. We have a very interesting website. Here is the link for the website. You can go and check our available services, which are all available through our website. Here is the website. You can see a screenshot from it. I'd like to encourage you all to visit this website and to check out all the services and courses that are available on it. We conduct different internship programs for students from Lebanon. We have already conducted 3 or more of these internships for different groups of students, which are very happy to visit Egypt and go for some field trips and visit some service companies here in Egypt, like Tomberger, Baker Hughes. I'd like to encourage you all to join us in any of our courses to become an ambassador and enjoy your discounts and all of other services that we provide. Just very small and short notes. To get the best of this webinar, please, I already muted all the participants, so please don't share your camera to be able to view the screen clearly. If you have any questions through this webinar, please drop it in the chat box, and I will read it loudly to our instructor for today's webinar, and he will be happy to answer all your questions. Please use your full name as written in your registration form to get your certificate with the name that you prefer. We will send certificates for this webinar in like 1 week from today. Thanks a lot for listening for this short presentation, and sorry for being too long. One last note that I would like to welcome our instructor for speaker for today's. 1 minute, please. Our instructor for today's webinar is Engineer Islam Fawaz. Thanks, Engineer Islam, for joining us and for sharing your knowledge with us. Engineer Islam Fawaz is a senior reservoir engineer with more than 12 years experience with Gulf of Suez Petroleum Company. And he has a demonstrated history of adding value through field evaluation and asset management, mainly tasked with looking after offshore fields in Gulf of Suez and field development plans. He is a highly skilled person in field development, water flooding, reservoir simulation, and reservoir management, and he is leading a high-performance team. Engineer Islam, the mic is yours to start the presentation and share your screen.
Thank you, Sam, for taking the time to be here with us, and I'll share my screen now. Can you hear my voice, please?
Yes, your voice is very clear, and you can start.
Okay. Please, can you give me access to share my screen?
Yeah, sure. Just 1 second. Can you try now, please?
No, I can't.
Try again, please. I just enabled it.
Not enabled.
There is a box in the bottom of the screen which is share screen. Please click this button and try.
Your browsing is preventing access to your share screen.
Okay.
Can you help me for this point?
Are you downloading Zoom or just using it from
the browser?
Oh, do you have the application or not?
Yes, I have.
Okay, so can you join us from the application, please?
Okay.
Hello, Engineer Islam. Are you sharing your screen now? Hello, Engineer Islam. I see your screen now. Can you hear me?
Yes, can you hear me? Yes, can you hear my voice?
Yes, I hear your voice. Yes,
Yes.
go ahead. Yes, go
Yes.
ahead.
Thank you, Assam, for taking this time for to be here with us, and sorry for this interruption. And you are welcome to our webinar today regarding pressure transit analysis fundamentals. Um, for I wanted to spend more time to talk about my background, but I'm really focused to say with you every piece of information which is viable today is related to someone who share his knowledge with me. So with some conference and some webinars, and so you need to rely on the conference and the webinars and some talking about the fundamentals in every topics. So our content today will talk about the introduction about the pressure transit analysis, and then we'll step back and going through what is meant by production data analysis, how to integrate the production data analysis in your field development plan, and we'll go through theory and the concept of the pressure transit analysis, and then we'll go to the input output from the PTA, and finally we'll talk about the component of the well test and interpretation model in pressure transit analysis. So when you ask a question, what's meant by well test? Well test is a joint analysis of measuring the bottom hole flowing pressure and the production and injection rate over the time in order to get or track record the reservoir state in terms of the permeabilities, and you need to define the boundaries of the reservoir, and you need to define the well or the completion properties. If we have something like skin and something like this, we define from the production from the PTA, from the well test. And this only method mainly rely on the transit state, which is means the wave doesn't hit any boundaries, which is mean aquifer, which is means this is a boundary, we have a fault, this is called boundary, change in the thicknesses, something like this could be affected in the pressure transit analysis as a boundary system. And the most important point when talking about the well test analysis is to integrate the data with other discipline. Don't work on your island. because well, pressure transit analysis, you can interpret different models, and you can interpret different model. You have different scenarios, so we need to integrate this model with other discipline like geology, like petrophysics, like and the fluid characterization, in order to incorporate all of these points into the simulations model and reduce the uncertainty in your reservoir. So when you ask your question, I can get from the pressure transit analysis the productivity, and then I can get the connected volume. So what is the difference? Now I have a well, and I have the bottom hole following pressure, and I have as a rate. After that, dividing the rate by the delta B, we have the productivity index of the well. So what is the difference between this and the well test? How to delineate this from the BI? BI, as I said, is the productivity index for the well, which is the rate over delta B. The rate which incorporate different parameter like permeability, like the drainage area of the reservoir, like the skim factor. All of this are lumped in one parameter, which is called the productivity index of the well. So the productivity index from the well test, we can define how the well is good or how the well is bad, because we need to discriminate between the skin that you have in a well and the permeability. If the well is producing good, it's okay, we use the permeability. But if the well has a bad performance, how to discriminate between the bad performance? Is this related to the permeability of the reservoir or related to the skin? From the well test analysis, we can discriminate between this. Also, we need to delineate it from the material balance itself. From the material balance itself, the reserves allocated for the well started from the initial reservoir pressure until the reservoir pressure is depleted to the current reservoir pressure. We produce some volumes, and this volume, this by running the material balance, this is the connected volume. So what is the difference? From the material balance, we can get the connected volume. From the well test analysis, we can get the connected volume. But the difference here, how the connected volume is distributed from the reservoir, since we can define it from the material balance, from the well test analysis. So well test analysis is a tool used for reservoir characterization and mainly based on three-phasic principle. First one, which is the material balance concept. Second one, which is Darcy law, which is relating the pressure and the flux of the well. And the third one, which is equation of state of the fluid. So well test objective, what is the objective of well test? Objective of well test is used mainly to define the reservoir limit. If we drill a well and we have exploratory wells and we have a sand, I need to define the boundaries of the reservoir, how much connected volume with the reservoir. So we run the drill stem test to define the reservoir limit test, the distance to the boundaries and the drainage area for this. Second one was production. We need to define the average reservoir pressure from the well test. We need to characterize the reservoir in order to characterize it for the simulation or impose this for a simulation model. We need to define the permeabilities from the well test. We need to define the completion efficiency from the well test. We need to define the skin factor. We need to define the reservoir model. We have a layered reservoir or we have composite reservoir. We need to define the contact. We need to define the gas contact. We need to define the condensate banking from the well test. We need to diagnose the productivity problem from the well test by defining the permeability and the skin. As I said in the first slide, the productivity index is a lumped single parameter which reflects the state of the reservoir. But from the well test, we can define this performance is related to the permeability or related to a skim factor. The last one, we can define, evaluate the simulation treatment. We need to find the skim factor, find the fracture half length of the reservoir, find the fracture conductivity, and so on. So for pressure transit analysis, we have main three regions. The first region, which is the early time region. From this early time region, we can define the skim factor or the partial penetration or the fracture conductivity. With some distance increasing the pressure wave with distance in the reservoir, we need to define the permeabilities. This is related to the permeability. And after hitting the boundary, we define the volume and the reservoir pressure. So how do we test a well? Testing well just to create a step change in rate, for instance, in case of we making a pressure build up, shut-in producing well. In case of making the rundown, opening shut-in well. In case, if you performing follow-up test for injector, we closing following well or injection well. So as you see here, we have designed the well to produce with a constant rate. After that, we shut in the well. After we shut in the well, this is the corresponding bottom hole flowing pressure, because due to this production, after we shutting the well, which is the pressure will be increased. We analyze this point. Analyze this point to refer to the productivity or the characteristic of the reservoir itself. Okay, so testing the well just to create a step change in the rate and measuring the response due to this step change in this rate. So as I said, this is well test sequence here, and this is the graph showing the pressure profile, and this showing the rate profile here. Just first, we produce the well as constant rate, because this, why constant rate? Because constant rate to measure the constant state of the reservoir. If we have variable rate, we can tackle this point by superposition. We'll talk about what means by superposition. So this well is producing with 600 barrel per day, and this is the corresponding bottom hole flowing pressure. If make a step decreasing in the rate here, which is means the pressure will be increased a little bit. This is the corresponding increasing in the pressure. We make a step change in the rate up, like the well is producing 5,000 barrel per day. The corresponding pressure will be decreased something like this, and shorten the well and analyze this increasing in the reservoir pressure. So this is the consequence of the rate history of the well. We have different flow period here, and we analyzing this increasing in the reservoir pressure, because analyzing this point is subjective to the rate history you are performing for the well. Just make a rate history for this reservoir, producing the well at rate or constant rate, and then shutting the well to measure the disturbance that you are putting for your reservoir or make for your reservoir. The second point we need to talk about, which is meant by production data analysis. Production data analysis, as you can see here, we have three main portions of the production data analysis: well test analysis and decline curve analysis. And we have, as you show here, we have overlap between the well test and decline curve analysis, which is the rate transit analysis. And we'll talk more about this in the next slides. So what is meant by production data analysis? Production data analysis is the science and art of using information about the reservoir and completion and or surface operation based on continuous interpretation of the data, like bottom hole flowing pressure and the rate. Based on that, we can give another information about, or we can give information about the reservoir characteristic, like permeability, like fracture properties, like the connected volume. Also, we can define the reserves and can help us for the production forecast. Also providing scientific support for reserve editors, selecting the best candidate for production optimization, and also help to you assure the input parameters for the reservoir simulation. As you can see here from this plot, we have three main portion of the production data analysis. The first portion is pressure transit analysis. As you can see here, is a standalone, and the decline curve analysis also is standalone. We can get from the pressure transit analysis the connected volume, OIB, and or the connected gas in place, and from the decline curve analysis we can get the UR for this well for the reservoir. But as you see here, we have overlap between the rate transit analysis and production transit analysis and decline curve analysis. We can get the same information here from the decline curve. We can give the UR as you can get it from the decline curve analysis. We can give the oil in place as you can get it from the pressure transit analysis. So what is the difference between all of this? The difference between all of this, between pressure transit analysis and the rate transit analysis, is when no shut-in is required, because rate transit analysis don't require shut-in the well. Just we have a permanent gauge, or you have the bottom hole flowing pressure, continuous measurement of the bottom hole flowing pressure and the rate, and after that you can get the data about the reservoir characteristics. For the decline curve analysis, we can get the connected volume from the flowing material balance. So what is the difference? From the rate transit analysis, it's based on the physics, it's based on science, it's based on the data. But from the decline curve analysis, this mainly based on analog. This mainly based on empirical correlation. Fitting the data, after fitting the data, we can get the EUR connected for this well. So in conclusion here, decline curve analysis is empirical equation, and the rate transit analysis is physics, based on physics. So for the decline curve analysis, what we are getting from the decline curve analysis is developed by ARBS. Just we have a rate history, don't require a bottom hole following pressure. Fitting is a rate history. After fitting is a rate history, we can get the EUR for the well. And the dilemma here and the language of the reservoir engineer is a P factor. It means P0 equal for exponential, B1 equal harmonic, and B between 1 and 0, which is hyperbolic. This is very, very important because it's mainly B factor in physical meaning. It's mainly depend on the drive mechanism. If we have depletion drive mechanism, which is mean we have severe decline in the pressure, like B factor is equal 0. But we have support for the reservoir, the B factor will be higher, and by then the reserves will be higher. So mainly for the decline curve analysis, just fitting the data. After fitting the data, we interpret this data. What happened in the past will continue in the future. After that, we can get the production forecast and get the recoverable reserves under the operating and current condition. So again, decline curve analysis is empirical decline analysis, and the main golden rule for the decline curve analysis: whatever the factor controlling the decline in the past will continue to control the decline in the future. So we have two main factors which will affect the decline curve analysis. One factor related to the reservoir condition, which is the depletion. Another one, which is number of well. If we have higher number of well, which means the decline would be more, we accelerating the reservoir. The drive mechanism, if we have depletion drive mechanism, will have steering aquifer support. This will reflect on the decline rate of self. Reservoir characteristic in terms of the permeabilities and the porosity and the phase distribution with the reservoir, and the saturation changes and the relative permeability. And the another factor is related to the operating condition. Operating condition like changing the artificial lift, choke size, back pressure on the well, operating our separator pressure. That's why when you are performing a decline curve analysis, some companies performing the decline curve analysis on the CD rate, and other companies performing the decline curve analysis on a BD rate. So the difference between CD is calendar day, and the BD is number of hour, which is well is putting on the protection. And the another important point we need to say for you is non-uniqueness for the decline curve analysis, because now we have a data here, something like this. 1B pessimistic in its nature, and we can perform a decline curve analysis here, and you say this is an x-axis that you are for this well. One a little bit optimistic and perform fitting the curve, and perform another decline here and showing the reserves will be higher. If you are more sunshine in your step and they perform decline curve analysis, which is mean hyperbolic, something like this, the EUR will be higher. So every point on x-axis has a consequence. The consequence, you need to drill a well, more wells in the reservoir or not, and this will be a higher impact on the decision and higher impact on the business. So all of these are equally valid because we are fitting the parameter. That's why when you're talking for the decline curve analysis, this is empirical correlation. If you have a data, and if it's a data, what are the factors that happen in the past will continue in the future, we have a different or possible scenarios, because this is just empirical, doesn't depend on any physics. So for decline curve analysis, yes, it's easy. We can do it. One from the advantage, very simple, very rare indication of the very rare indication of the well performance, but we have a limitations for the decline curve analysis. From its limitation, we assume we have constant operating pressure. We assume the reservoir pressure is performing constant way. We are assuming the reservoir reaches the boundaries itself. in transit, we cannot perform the Klein curve analysis because we are in transit way. But once the wave reaches the boundaries of the reservoir, which is mean that we have in boundary dominated flow, we can apply the decline curve analysis. Also, the main limitations for decline curve analysis is non-uniqueness result. Every engineer SLAM performing decline curve analysis, any other engineer perform decline curve analysis, everyone we can perform decline curve analysis, and everyone we can get a different number. All of those number are possible outcomes. So this we have non-uniqueness result, particularly if we have a lower permeability reservoir or lower permeability splay. But when you have a low permeability reservoir, as I said in the pressure transit analysis here, just produce the well and constant rate, and then make a step change, shorten the well, and measure the response of increasing the pressure here. But if we have a low permeability or nanodorsal permeability, how to characterize the reservoir? So we need to think about a different concept. How to characterize the reservoir in low permeability reservoir? We can use rate transit analysis. Rate transit analysis is the same principle of the production of the PTA, but is mainly focused on the late time region, mainly focused on the boundary dominated flow. Okay, this is not replaced for the PTA in all circumstances. Just we have a bottom hole following pressure continuous measurement, and you have a rate, we have a single phase in the reservoir, and then we can perform the rate transit analysis by different graph. As I said in the first slide, yeah, science and the art. This is art because we have log plot, we have a square root plot. All of those plots just to give more insight about the data itself. So we have a specialized plot in order to give more insight about the reservoir characteristic or about the boundaries of the reservoir. And after that, we can integrate all the valuable information together to get more insight about your reservoir. One of the most important points that I want to show for you for the pressure transit analysis is it's run at constant rate or constant rate. Why constant rate for pressure transit analysis and rate transit analysis? Because as you see here for this graph here, this is the well here, this is no flow boundaries here, and this is the pressure wave. If we produce the well at constant bottom hole flowing pressure, which is means the bottom hole flowing pressure is constant here and the rate is decline. So the pressure wave will moving forward something like this till we hit the boundaries of the reservoir. As you can see here, this is the pressure tend to go down, go down, go down, go down, something like this. But for constant rate, we have, if we producing the well at constant rate and the pressure will hit the boundary, after that the reservoir pressure will be declined. We have constant delta B decreasing at the bottom at the perforation, which is mean by this, when we're measuring the bottom hole following pressure and the reservoir reaching the Boussier-Dussel state, we can tell you from the bottom hole following pressure without shutting the well what is the reservoir pressure. So rate transit analysis is the fundamental, this equation or Boussier-Dussel state is the fundamental for rate transit analysis. We can solve it, the rate transit analysis for single phase above the bubble point pressure, because we have constant flow properties like density, viscosity, we have constant compressibilities, but in gas system we have more complex and we need to some correction for the pressure due to because the fluid will change heavily when we have a higher pressure for the gas. But in case we have a variable rate, we can handle this variable rate by superposition for rate transit analysis and for pressure transit analysis. So we have two components for the rate transit analysis. One component is the inflow parameters, which is coming from the Darcy law. As you related the difference in the pressure due to the influx, we have the average reservoir pressure and the bottom hole flowing pressure and plus Q plus PSS. We'll talk about this in more detail. Plus depletion term, like the compressibility term, like we have volumetric reservoir. This is coming from this point. After that, we're integrating the Darcy law and the material balance equation in order to get the Boussier-Dussel state condition, which is mainly used for the rate transit analysis. let's come into inflow term here. As you see here, this is well, and this is the boundary of the reservoir here, and this is the bottom hole flowing pressure, and this is the average reservoir pressure, and this is the B star or B reservoir, B initial reservoir pressure, or B star. So what is meant by inflow properties or inflow term here? Inflow term here, as you know, this is Darcy equation, Q Ka B bar delta B over mu L. If we arrange this equation in terms of the pressure here, which is mean P bar minus bottom hole flowing pressure equal Q, and this term is called PSS, precious state, which is the 1 divided by the productivity index. As I meant here, I wanted to tell you here from this graph that when we have a pseudo steady state and we have a constant rate, and we have with time the first point in time here bottom hole flowing pressure, and this is the pressure wave of the reservoir at the boundaries of the reservoir. With depletion in this reservoir, the bottom hole flowing pressure will be depleted. By knowing this shape, we have constant delta B from here to here, and also we have constant delta B from here to here. By knowing the bottom hole flowing pressure, we can infer that about the connection, the reservoir pressure without shutting the well, and we can infer from the flowing material balance the connected volume of the reservoir. This is what's meant by inflow term. But in case of the depletion term, like a material balance, we have at initial state of the reservoir, we have N volume. Once you produced a volume of the reservoir, what we are producing is NP. What we are remaining is the initial volume minus what we are producing. This is what are remaining in the reservoir. This remaining is what we are producing is related to the delta P that we have due to the production. This is due to the fluid expansion itself. The delta B due to fluid expansion itself. By putting this in the equation of the compressibility term, we have total compressibility, change on volume per unit pressure here. So this is the total compressibility here, and this is the original MN, which is the original stipend that you have. This is NB, what you are producing. This is BI minus P bar. If we rearrange this equation, you can get P bar in terms of the B bar, B initial minus MBSS and NP. By combining the two equations together, inflow in terms of the average pressure, this is inflow equation, and this is depletion equation, we can get this term. At constant rate, we can refer the depletion in the reservoir pressure by this equation. So by knowing the bottom hole flowing pressure, I knowing this from the history of this reservoir, you can get the characteristic of the reservoir. This is what's called flowing material balance. From the bottom hole flowing pressure, you can get information about the average reservoir pressure, and also you can give the information about the connected volume within the reservoir. If we have variable rate, we can handle this point by superposition. So rate transit analysis is one of the pressure, one of the production data analysis that combines the pressure transit analysis and decline curve analysis. We have overlap between this pressure transit and decline curve analysis. Combining Darcy law and equation of state and some material balance, we can give information about the reservoir and well. This is not replaced for the PTA. This is just for the production data. How to analyze this data? As I said, by knowing the bottom hole flowing pressure, continuous measurement for the bottom hole flowing pressure and the rate, we can convert this in single variable normalized rate and put it in the material balance time on log scale, and also we can derive the type curve and can derive the characteristic of the reservoir. This is what I want to see for you, the final message or the key takeaway from this presentation here, the integration of the knowledge. As I said, well test analysis is highly resolution because mainly focused on the unsteady state condition, and you can get from this about reservoir characteristic, permeability and the skin. Also, you can get from the transit analysis permeability and skin. Also, you can get the connected volume. Also, you can get the average pressure. All of this we can get like from the well test, and you can get it from the production data analysis or RTA. But RTA is performance based on the recovery factor, not the decline curve analysis. Decline curve analysis is just based on the empirical equation, just fitting the data. After fitting the data, you can derive the UR, and after that, you can based on empirical equation. So doesn't take in your consideration, we have a depletion derived reservoir, the abandonment pressure for the reservoir. If we have a decline curve analysis and you perform the decline curve analysis for depletion derived reservoir, just fitting the data and don't take in your account the bottom hole fluid pressure. But for rate transit analysis, taking in your consideration the bottom hole fluid pressure, that's why this is projection of the recovery constrained by historical operating condition, considering taking the historical operating condition in your consideration for the rate transit analysis. This is a difference between RTA and PTA. PTA, as I said, control state of action, open, shut in the well, to send signal into the reservoir. This signal give fingerprint about the reservoir and give information about the reservoir characteristic. But for the RTA also use the same, just don't shut in the well, just the well is opening, and measuring if we have permanent downhole gauge and measuring the bottom hole fluid pressure and the rate, you can get information about the reservoir. And also if you have some accident in well, like the well is shut in due to operational problem, you can get this information because we have a free well test. You can make a bottom hole or like a PTA, free pressure transit analysis. The same principle use the Darcy equation, continuity equation, and the material balance to give information about the reservoir. But the main different point here, or the main key point from this slide here, is for rate transit analysis is low resolution, low frequency, or low pressure. You can give pressure data every 1 month. But for the pressure transit analysis, I need the pressure data every seconds. So low resolution data, low frequency. We can lump 2 years or 3 years in the same plot. But for the pressure transit analysis, mainly focused on a steady state condition. So pressure transit analysis and steady state condition is the main interest. Rate transit analysis is the boundary dominated flow is the main interest. This is the synopsis of this well test analysis. Here you can get from the permeability. Also you can get permeability from the core. Also you can get permeability from the open hole loop by correlation. You can get permeability from other estimate the permeability or from other logs, but pressure transit analysis give in situ permeability. Not permeability is called flow capacity, KH over mu. Also, we can update your structure. You can tell the geologist how the volume is connected from the pressure transit analysis. Also, we can define the average pressure on the reservoir. This is what is the objective of the pressure transit analysis. I need to talk about some concept about the well test here. This is very important because well test analysis or the production delta analysis is mainly depend on two concepts. The first concept, which is constant pressure, and second one, which is constant rate. This is called reservoir signal. Reservoir signal is a combination of two concepts. If we keep the rate is constant for a short period, you show that the pressure will bottom hole flowing pressure will be decreased from this point to this point. This means this is solutions for the diffusivity equation. For constant pressure here, if we keeping the bottom hole flowing pressure constant for a short period, you show the rate will be declined from here to here. This is the constant pressure solution. What we are using for the pressure transit analysis is constant rate solution, because and the rate transit analysis is constant rate solutions, because as you see here from this graph, delta P in the boundaries will be reflected in the well locations here, and you can tell you from the rate transit analysis the depletion in the pressure, and from the bottom hole flowing pressure the average pressure without shutting the well, and define the connected volume with the reservoir. So transit flow, this is happen at initial condition of reservoir. the pressure will propagate it into the reservoir until hit a boundary. From the transit state, we can define the skin, define the permeability. Once we hit the boundaries of this reservoir, this is the boundary of this reservoir, we can define the connected volume of the reservoir. We can define the initial reservoir pressure. Just this wave is a fingerprint of this reservoir, like we are performing some X-ray. This is a fingerprint of you. So this fingerprint contains information about the reservoir characteristic, which is main your interest. This is the equation that will be used for the divisivity equation, like line source equation. Just we have bottom hole for longer pressure. We have a rate here. Enter those parameter. We can give the characteristic of the reservoir, like permeability and like flow capacity of this reservoir and the boundaries and the skin. So imagine the pressure profile during the build up. Once we shut in the well here, we shut in the well is producing with constant rate and then shut in the well. Imagine what will happen when we shut in the well. This graph showing the distance from the well pore, and this showing the pressure, how the pressure is built up. The first one at time 0, this is the pressure, which is currently the bottom hole for longer pressure, once at time 0. Increasing the time here, which show here the distance, the pressure wave will move farther away from the well pore. And after that, at time, at 1 hour, the pressure wave will move 1 hour. Within 1 hour, will move 100 feet from the well pore. And after that, 100 hour, which is move 1,000 feet out from the well pore until the pressure is stabilized and reaches the boundaries of the reservoir. So this is the pressure wave or the radius of investigation. Once we shut in the well, we have the pressure will propagate it into the reservoir until reach the boundary. After that, we can define from this pressure curve the characteristic of the reservoir. Once the reservoir reaches the boundary, this is the pseudo-stress condition. We need to define the volume, how much volume we have, how much connected volume we have. This doesn't seem by the material balance. Material balance shows the connected volume, but how it's connected with the reservoir, you cannot tell you. Could be the oil distributed laterally, could be the oil distributed vertically. We don't know. From the pressure transit analysis, we can define, and rate transit analysis, we can define how the volume is connected within the reservoir. So this is a puzzle for its investigation here. We have two wells. First well is producing with 100 barrel oil per day, and second one is producing with 5 barrel oil per day. This is impact the radius of investigation. This is the equation of the radius of investigation. The answer the same. Why? Because the rate is not related to the radius of investigation. As you see here, the radius of investigation term is related to the permeability of the reservoir. This is the speed, how the wave is the speed of the wave moving out into the reservoir or moving into the reservoir. This is called hydraulic diffusivity. This term is affect the well spacing and simulation. All this term like permeability, porosity, viscosity, compressibility, this term will be affect the well spacing and simulation itself. So radius of investigation here just depend only all of 4 parameters: permeability, porosity, viscosity, and the compressibility. Doesn't relate to the rate. So what is the input for the well test, and what is the output from the well test? The input from the well test here. So go to the equation. You can see here what is input here. The input here is a porosity. Yes, this is input. The first input, which is bottom hole for longer pressure and discretized rate. This is the first input. Second input, which is the flow properties. As you see here from the equation, mu, compressibility, radius of the well, porosity, and also the well model or the interpreted well model. Type of the completion, is the well deviated, slanted, is the well horizontal. From this and type curve analysis, we can give the information about the reservoir, like flow capacity of the reservoir, can give information about the skin, the average reservoir pressure is there is a barrier or a baffle or a change on thickness in the reservoir, or you have multiple layers, we can define it from the well test analysis and also the well model parameter. This is the main input and this is the main output from the well test analysis. This graph, I'd like to just summarize the input as the output from the well test analysis. This graph showing superposition time and the pressure differential, or you can put the pressure data, and this is the pressure curve, delta B curves, and this is the derivative of the delta B curve. From the derivative, reflect information or reflect the state of the reservoir and the state of the well performance. From this point here, we can this hump is reflect the skin, and this also not reflect the permeability. Don't say permeability, say reflect the flow capacity of the reservoir, KH over mu. If we have a change in mu, this curve will be act as a boundaries. If you have a change in H with space, this act as a boundaries in the derivative itself. So this increasing, this line reflect here. If we seeing here, which is mean the infinite acting radial flow, this is investigation at this time. If we have some data like this, so with this x-axis, which is mean we have increasing in the distance here and also increasing in the radius of investigation. So this is the main point of interest for the these curves. So finally, we'll talk about well test interpretation model. What is the interpretation model for the well test? We have three main regions for the well test. The first one, which is well pore storage region, which is near with the well pore. Second one, which is the middle time region, which will reflect the reservoir characteristic, and after that, the boundary or the late time region, which is reaches the boundaries of the reservoir faults or aquifer or a change in the H, which is the thickness of the reservoir, or a change in the fluid, which is oil or gas or water and something like this. We have three main stages. The first one, which is model identification. Before we performing any pressure transit analysis, you have to identify which model you have. So for early time region, you need to define we have well pore storage or not, skin or not, we have fracture, we have partial penetration, you have horizontal well or not. All of these are model identification. For middle time region, we can define we have homogeneous reservoir, we have double porosity reservoir, a composite system, or have to layer reservoir. You can define this from model identification. For the late time region, we need to define we have a boundaries. I need to design a test in order to define is there is a nearby boundaries or not, in order to define the gas contact, in order to define the condensate banking. So model identification is the first point before we are performing a well test interpretation model. After we performing all of this, define the near well pore effect, define the reservoir behavior, define the boundary effect, we are interpreting the model. The second one was go to parameter estimation. How to estimate the parameter? How to get the H of the reservoir? This is DSCT from the open hole log. How to get the PVT and support the PVT, the well model from the data that you have. Put this in your model and give a first guess estimation of the initial parameters that will be input for the software. After we put the parameters here and identify the first model here, we run the model based on the observations that you have. After that, we get the result. Is this result consistent or not? And also ask yourself, is there a possible another solution for that? Because some result could be some data could be if we have a data and we have increasing in the derivative as a boundary, you can interpret this with different models. So this model should be matched with the geological concept, should be matched with the reservoir state, should be matched with our understanding in your reservoir. So again, the key point from this, you need to define, we have three main region. First region is a well pore storage, which is unwanted. I don't want to see well pore storage, because well pore storage is reflect the pressure loss in the well pore, not the reservoir. I run a pressure transit analysis to characterize the reservoir, not to characterize the behavior of the well pore. After that, we going farther into the reservoir and see the original permeability of the reservoir, the original KH of the reservoir. After that, I need to define if there is any boundary, if there is a closed system, we have 4 faults, if we have a channel, if we have two intersecting fault with angle, if we have a change in a fluid, like we have the gas contact, I need to monitoring the gas contact with time. You can run a pressure transit analysis. You can define it from the pressure transit analysis. The interpretation method for the PTA, we have 3 interpretation method for the PTA. We have a straight line method. We have plot method. We have type curve method. From straight line method, just I say it in the first slide, science and art, just mathematics. Doesn't relate to mathematics. We have a pressure data, and we have bottom hole flowing pressure data, and we have rate data, and by perform some chart in order to define the flow regime of the reservoir. And this is the summary. If we have well pore storage effect, delta B over delta B, showing as this graph as a line here, something like this. If we have fracture reservoir, if we put delta T power half versus delta B, you can show high fracture, and so on. For limited entry, you have to stabilize limited entry, which is mean partial penetration. We have to stabilize. The first one is stabilized for the thickness for the reservoir, and the second one was stabilization for the total thickness of the reservoir. So we have some plots, and some from this plot we can help you to give more indication about the near well pore effect, about the reservoir behavior. If we have double process system, this is, you can define from 2 parallel line from the double process system. We have one and one, or you can call it S shape. If we don't have a double process system, and you can interpret the fault as a double process system, but from this graph you can make it definitely this is related to the 2 parallel fault, or related to the porosity double process. From the 4 boundaries, when the pressure wave hits the boundaries, you can define from this plot the by plotting delta B versus delta T, we have double slope. You can find this is single fault. We have a channel showing half a slope, and something like this. For log plot here, I will talk about this point in the next slide. And type curves, this mainly used for, which is log plot. The difference between different interpretation, like log plot, and I said sorry, this is kangaroo. And what's meant by kangaroo here, if we have a kangaroo and put this kangaroo instead of A4 sheet, you can put it in rubber sheet, and stretch rubber sheet in vertical axis, and stretch rubber sheet in horizontal axis, and you can give another information about the reservoir. So this is if you have bottom hole flowing pressure and the bottom hole flowing pressure in linear plot. This is the original state. We can know more detailed about the reservoir here. But if we put it in the logarithmic scale, if you have the time here and the delta P on log scale, and stretch it in the x-axis here, which you can define how the speed, you can measure the speed, how the speed of the kangaroo is moving. But the main beauty here for the kangaroo here is the derivative here. If we stretch it or distort the data in some kind like derivative here, you can tell you the kangaroo has a baby here. So we have a data, and with the mathematics, we can give more information about the characteristic of the reservoir. So from this data, we're measuring only from the build-up about 10 psi or 5 psi. From 5 psi from the bottom hole flowing pressure to reaching the boundaries, or 6 psi. So we can determine from this data from 6 psi the characteristic of the reservoir. But the main drawback of this plot here, if we have erratic data, if we have data masked with the well pore storage, we can determine anything. If we have low resolution of the gauge, we have phase segregation. You're putting the gauge in shallow depths. Sometimes will be affected in your interpretation. Okay. So don't simplify the 2 point. Don't simplify the rate history, because the rate history has plays a major impact for your interpretation if we are analyzing the boundaries of the reservoir. Thank you very much for watching my webinar. And if you have any question, I'm ready. Thank you, Assam. Hello.
Thank you, Engineer Islam, for this fruitful and very informative information and this powerful presentation. Thank you so much for being with us today. I really admire your presentation so much. I will be sending a feedback link for this webinar in the chat box. So please take a minute to fill in this feedback. While also send your questions in the chat area while filling the feedback, and we will go after that for the question and answers part of the webinar.
Hello. Any questions? Okay.
Please drop your questions in the chat area, and I will read it loudly to Engineer Islam to answer it. Seems like the presentation was very clear, Engineer Islam. We don't have questions till now.
Okay. Thank you. I will type any question. If we have any question, say something. ونمشي بقى ولا
comfortable. Thank you.
Okay, thanks again, Engineer Islam. Seems that we don't have questions now. Uh, Thank you everyone for joining us today, and we'd like to see you all in the next webinars. I will drop the links for the registration for our services, courses, webinars, and for the mentorship program, so that if you'd like to join us in any of the courses to know more information, like the course for pressure transit analysis, if you are interested in more analysis information, you can join us.
Thank you very much and see you.
See you.
See you. Bye.
Bye.